Okay, let's get started. Good. Oh, no. Okay, so this is the second lecture about multi-rotor dynamics control, and it's also the last lecture of this course. So in today's lecture, we will cover position stabilization control, path following control, and also I'll go over some steps about how to set up a commercially available drone. Okay. So before that, we'll do a little bit of recap about some of the contents in last lecture. So in the last lecture, we talked about the dynamics modeling of a planar quadrotor, so in a 2D motion. So this is a complete state of the system, and by Newton's second law, we can construct the dynamics in this format, so which is a nonlinear dynamics. And by using some by either doing it manually or using some tools, we can get the linearized model of the system, which will give us opportunity for later control design. So the reason why we do linearization is that because linearization gives us a simplified version of the dynamics around the equilibrium. So then we have abundant tools to decouple and design the controller. Okay, so the procedure I explained last time is just by taking the Jacobian of the system. So if we have the Jacobian of the system, for example, partial f partial x and partial f partial u, then we can evaluate the Jacobians at the equilibrium to get the AB and also CD matrix. Okay. I also presented some ways numerically or symbolically using MATLAB to obtain such a linearized model. For example, you can use a symbolic toolbox and in conjunction with the Jacobian function to get the final result in the symbolic format. And then you can evaluate this symbolic format at the equilibrium to get the corresponding matrices. And in addition to that, you can also use a Simulink model and also the function called the limod to get the linearized model around the equilibrium. Okay. So both of them will give you the same results. Okay, so any questions so far? Okay, good. Okay, so begin today's topic. So after we obtaining such models, and then how do we design a controller to stabilize the quadrotor to a given position or given path? So the main methodology introduced in this course is called the PID control. So I assume some of you have already familiarized with this concept. So basically, what it does is that we start analyzing a simplified system. So it's something called a single input, single output system. And also it's in the so-called double integrator form. So we have for x double dot equals to our u. So basically, this is like a point mass. So we can control the force of the point mass, so that we, by designing such u, we can control the velocity as well as the position of the point mass. And in order to control the position, we define something called the position error, so which is E. So we have the desired position minus the actual position. So our control objective is to design such a U, such that our E goes to 0 as time goes to infinity. Okay. And how do we do that? So if we want the error to goes to 0, maybe this error and also the derivative and the second derivative of this error form something called a stabilized second order system. So if you pick a KV and KP properly, then you have a transfer function of this simple system with input at 0. So if you pick a KP and KV properly, by some kind of fundamental series of linear system, you can arrive at some kind of stable system. So if your input is 0, then your output or the states and its E will eventually converge to 0. So then what we do is that, okay, since we want the E to behave like a stabilized second order system, now we plug in a definition of E. So which is x desired minus x. And then we can arrive at this dynamics. So we have this desired, so this is kind of a feed forward term. So it's like equilibrium acceleration in our case. And then the difference between the equilibrium acceleration and the actual acceleration is a function of the position error as well as the velocity error. Okay. So then by using the dynamics of the system, so we also know that x double dot equals u, then we can replace x double dot with u. Okay, so basically this one is u. So now eventually we'll arrive at this term. So basically it gives you some kind of the so-called PD controller. So the first term is a feed forward term. So if you want your point mass to do some kind of acceleration and deceleration, then you need some kind of a feed forward force. Right? That's kind of an equilibrium force. And in addition to that, if the point mass moves away from the equilibrium you designed, then the E dot and the E will be non-zero. Okay, so those additional error will contribute as additional force to drive the system back to the desired trajectory. Okay, any questions? Good. So yeah, so this is called feed forward term, derivative feedback, and proportional feedback. So that's why we call this as a PD controller. So PD controller you can view in terms of electric circuit. From electric circuit point of view, you can view the proportional gain as the capacitance. The derivative control is the resistance. Basically, it's like a damping force. Right? Capacity force is like a spring to move the system, and the D term is to eventually damp out the excessive velocities. And more often, your system is not going to be solely driven by your control force. So quite often it will be affected by some other disturbances. For example, for quadrotor, quite often we need to deal with wind gusts, right? So it contributes to additional wind disturbance. So in order to compensate for that, we need the so-called integral term. So basically, the idea is that if we do not have integral term, then we eventually will have a steady state error because of the external disturbance. But so if we integrate the error with respect to time, so we gradually increase our. So if we found so just by using PD controller, it does not converge to our desired location, we gradually increase our control input by using the integral term. So after a while, because we have some additional force to compensate for the disturbance, then the system will hopefully converge to zero. That's the idea of the basic PID control. Yeah, but also if you choose to use integral control, then you must be aware of some of undesired effects such as wind up. It means saturation of your control input. If the external disturbance is too large, it may cause a saturation in your input, and it will degrade your dynamic performance. So here are some typical response for PD controller with different gains. So if we pick a stable gain, so all of them are greater than 0, it will arrive at the given position, and given no external disturbances. And if there is no damping force, meaning if we do not apply any derivative feedback, it will just behave like an oscillator, harmonic oscillator. It will never settle down because there's no damping in the system. And if we do the controller in the opposite direction, it will go unstable. Okay. So then how to design such a KP and KV? Well, what we can do is that we use some kind of parameterization. So in the linear system theory, we have something called a damping ratio and a natural frequency. So for a system, we want to pick the damping ratios, for example, between 0.7 to 1. And we want the natural frequency to be around like TR, which is the rise time, divided by 1.8. So if we pick this TR, then we can calculate theta and omega, and then we can replace the individual games with this with those individual values to get a desired dynamic response. So this is a typical response diagram for the second order system. Yeah, I think that this should be covered in your linear system control course. So we have a rise time is at the time it takes from the 0.1 to 0.9, and the peak time is when it goes to the time that it takes to go to the peak. Settling time is the time it takes such that all the states settles within the 1% bound around the equilibrium. So if we pick, so this is a diagram of the effect of different magnitude of theta and omega. So usually from 0.7, this is a kind of desired response. So we should pick theta around 0.7, such that our system will have a very steady with no very aggressive overshoot. Okay. Okay, so here is a example I built in Simulink. So we just test our parameter tuning in a simulated environment. So this is how you build this second order system in Simulink. This is something called an integrator. So we have a double integrator. So this one is x. Sorry, not x. So we take the integration of the input once, and then we do it twice. So we get a double integrator effect. The controller is in some kind of PD form. So this is a proportional feedback. So we pick the goal as 5, and then we use this summation block to get the position error. So it's like x minus 5 is our E. And then we put E in as input of proportional feedback, and also we get x dot as our derivative feedback. Because right now the position, yes.
Sorry, can I just clarify? So you're using a double integrator because your U is x a lot, and you're trying to get x, is that right?
Yes.
So you're integrating twice?
Yes. Any questions? Any more questions? Yes.
Just from a KP and KD, is that something we're going for to have them equal to each other, or as long as they're above 0 and it
Yes.
depends on the system?
Yeah, good question. So as I said, so you have two ways to pick. So one is through this alternative for parameterization. So you can basically decide your omega and the theta to decide KP and KV. And another way is just to tuning by simulation. So you just try some values, empirical value. For example, you can try 1, you can try 10. And then because Simulink can give you the response very fast, so you can just by viewing the response, you can adjust the KP and KV. Yeah, good. So so for this example, I just pick a KP and KD to be equally to 4. And but this is not I will not say this is optimal value. So you can try other values. But this one is the one I tried in Simulink, so that they can give me a smooth response. Okay. So then I have some further experiments. So if we increase the KP to a very large value, so from 4 to 40, then you will immediately see you have a very large overshoot. So increase the KP too large, you'll get a large overshoot. So it means that if you set it too high, so if you set a KP and then you discovered, okay, the response curve has a very large overshoot, then maybe you need to reduce your KP a little bit. Or on the contrary, you can increase KD. So these two factors plays counter against each other. And if you pick a very high KD, then you will see, okay, so at the end of the simulation, at 10 seconds, it has not reached the goal yet. So if you pick a very large KD, then because you have a very large damping force, so you will have a system with very slow response. So here is a rule of thumb. So if you have something in your Simulink, you can try some KP and KV. If you want faster response, increase KP. But if you discover, okay, this fast response costs too much overshoot, increase KD. But if you have too slow response, then maybe your KD gain is too large. Questions? Good. Okay, so then we move to the integral gain. So as I said, for a typical for actual systems, you will not only have your control force, but also your disturbance force acting on the system. So here in the Simulink, I use a constant block with a value of 3 as some kind of unknown disturbance added to the controls. So the control does not know there's a 3, so it just controls as if there is no disturbance. So if we just use the original control law here, then you will see we'll have a steady state error. This one is the desired state, this is the actual state, so we'll have a steady state error. Okay, then it's time to use the integral feedback. So the integral feedback is adding as follows. I pick integral gain as a Ki equal to 0.3. So roughly 1/10 of the Kp. And now the response you will see, it will introduce some overshoot because of integral gain. But the benefit you get is that eventually the integral gain will eliminate the effect of disturbances. So the final state will eventually converge to the desired location. Okay, but if I increase the Ki gain to 10, so if we pick two overly large Ki, then you will see very large overshoot and very long oscillation time. So the settling time is very long. So the principle behind of choosing the integral term is that you should start with small values and gradually increase this value, such that this settling or this conversion steady state time is reasonable. So if you find your system is oscillating very aggressively after adding the integral gain, then you should reduce integral gain by a factor of 10. Good. Any questions about how to tune? Good. So rule of thumb. Start with the proportional gain first. Okay, so for the given system, you start with Kp. For example, for quadrotor attitude channel, so there are some empirical values for different type of systems. For quadrotor drone in the attitude channel, you can try 1. For example, if you want to control the roll pitch, your angle, you can try 1, 5, or 10, or something in between as a Kp. And you can pick the derivative gain. If we want to control phi, then the derivative signal is phi dot, right? So you can pick the phi dot gain equal to the proportional gain. So you start with this value. And if you observe steady state error, you start with an integral gain and roughly 10% of the proportional gain. And then observe the response. If the steady state error converges too slowly, you just increase a little bit. And if settling time is very, very long, try to increase the derivative gain. But to keep in mind that those tuning only be effective for very simplified systems, for example, linear systems. If your system has very strong nonlinearity in it, you need to use more sophisticated way to design a controller, rather than relying on PID tuning. Good. Questions? Okay, good. So after introducing the basic concept of a tuning of the PID, then we can use it in our first example. It's called the example we introduced last time. It's called a 2D planar quadrotor. And the task we want to do is that we have a quadrotor. So the most important task for quadrotor is to hover at a given location, either for surveillance or delivery or some kind of other missions. So the thing is that, okay, we want the position error to be to converge to 0, and also the velocity error to converge to 0 as time goes to infinity. Okay. So if we so here is the result of last time we got from the linearization. So it tells us something. So if we take a look at the last row here, we see that these terms are all 0. So it means that the attitude channel is decoupled from the translational channel. So it means that we can design the attitude controller first before we design the translational controller, right? Because this is only affected by the control input. So it's basically phi double dot is a double integrated system with your tau, right? And if after we get a controller to stabilize phi, and if we take a look at the remaining part, then we can say, okay, the y dot, which is horizontal motion, is actually affected by, because we have this minus g here, and this is on the second column, so it's actually affected by our phi. So if we can control the phi, then we can control the translational movement. So this gives us an insight of how to design the controller into such a cascade form. So here is a control diagram I introduced last time. So it's called cascade nested control architecture because of the decoupled nature of the quadrotor at its equilibrium. So basically, we can do this one first, attitude controller first, and based on top of that, we can design some position controller. And if we obtain the attitude controller, and by using the rotor thrust mixing algorithm we introduced last time, then we can get the thrust on each individual rotors. Good. Okay, so yeah, so this is some kind of detailed steps. You start with attitude control, and then you design a positional channel, and after that, based on the position channel, you can design some kind of higher level mission module. So this is a 2D quadrotor. So for the attitude channel, we use the PD type controller. So this is our double dot. So acceleration of phi, and we want the phi to we want the E, which is the desired phi, converge to our actual phi, converge to our controlled or command phi. We need to what we do is that you design attitude controller in this format. So basically, we have a feed forward turn, same as PD controller. We have a P gain, now we have a D gain. Okay, so we start with attitude, design a controller to stabilize the phi angle, and if phi angle can be controlled, then we can tilt the quadrotor to move back and forth. And then on top of that, we design this position controller, also using the concept of PD control. So then what we do here is that, okay, since so in the PD control, we treat the quadrotor translational motion as a point mass. And then if we have a horizontal position error, then we convert this horizontal position error into a phi command. So basically, if there is error between our design position and the actual position, we want the drone to tilt accordingly by using a PD type controller. Okay, so yeah, on top of that, so similar for Z, but for Z is that in our simplified case, we can use our lift to control the Z motion because the tilt angle here is small. So we can feedback the error between our desired altitude and actual altitude and convert it into a thrust command, such that we can adjust the equilibrium thrust a little bit to control the up and down motion of Quadrotor. Okay, that's a very basic concept of three controllers. One is to control the Z motion by using the lift adjustment. This one is a horizontal control motion by adjusting the roll angle. And finally, if we have the roll angle, we convert it to a lower level command to control the acceleration, to angular acceleration of the Quadrotor, so that the Quadrotor will tilt according to our command. Okay, so that's the control. So we control equations. So we'll go quickly to an example. So I built this model in Simulink. Then I also designed a PD cascade controller based on our previous methodology. And then I'll just see whether this methodology can actually work in a simulated environment. So this is a simulation model. Oh, so after this course, I will upload all the files on Quarkus, so you can download that and play with yourselves. This one is this upper block is the model. It's a nonlinear dynamic model, and the lower block contains all the controllers. And this is our target location. So here in the simulation, I set as 5 and 5. So it starts from 0 and 0, and we want the Quadrotor to fly to y equals to 5 and z equals to 5. So here is the nonlinear controller I built in Simulink. I also introduced last time, so you can download that later and read detail on your own. But it just resembles the previous dynamics we present in the linearization part. So in the control part, I also separated the attitude control and position control into two separate different blocks, representing this attitude control and the position control channel. So the attitude control is in this block, position control is in this block. And within the position channel, so as we explained earlier, so for the control of the position channel, we treat the Quadrotor as a point mass. And we design something called the virtual lift, so FD. So as you can see, we feedback the position, the actual position x, the desired position xd, and this is a KP, again here. And also feedback the x dot, and this is a KD. And here, because the target location is a fixed point, so the xd dot is 0 in our case. So I can simplify the control a little bit. So and then it resembles a typical PD control in the translation motion channel. So we forget about the attitude moment at this moment. We just design the force required to move the Quadrotor in the 2D space. Okay. And then this -1, of course, is a negative feedback. So we need negative feedback to stabilize the system. This is a saturation module. So this is for engineering practice, because for Quadrotor it cannot produce negative lift. So if this produces a lift which is too low, we should have a lower bound to bound the required lift. And on top of the motion to control the motion, on top of the force to control the motion of the quadrotor, this part is the gravity compensation. So basically, in addition to the force to move the quadrotor around, we also need a force to compensate for the gravity. So before we send this FD to the attitude controller, we add the control force with our gravity compensation force. So any questions so far? Are you clear with the design? Okay. So after that, we obtain something called FD. So it's our desired lift based on the current position error. Okay. So then what we do is that, okay, in the attitude channel, we have this desired FD. And then what we want to do is that, firstly, it does this. So it calculates the dot product of FD. So basically, it means that FD transpose FD. And here is a square root. It means that we take the norm of FD. So this is the magnitude of the lift we need to produce, right? So it's like the lift, the actual lift on the produced by 4 rotors. And then by dividing the magnitude of the lift, so we divide FD by the magnitude of itself, we get the ND. So this is a normalized vector. So basically it tells you where the quadrotor should point. So if we obtain ND, we use something called arctangent 2 function. Here. To get the actual roll angle. So if we have a vector, like it's tilted a little bit, so it corresponds to a roll angle of the quadrotor. And it is obtained by using the arctangent 2 function along with this negative 1 gain. So here, after this module, we get the phi command as we described in the previous slide. So this is our desired roll angle. And then after that, what we do is that we use a high pass filter to get a filtered result of our commanded phi angle. So it serves as a D command. So it's a derivative feedback. On top of that, we subtract the actual phi with our commanded phi. So here is a phi minus phi c. And this gain is a Kp gain, and this gain is a Kd gain. So in the attitude channel, we use the so-called PT controller. Okay, is that clear? And the reason why I use this high-pass filter is that in practical concern, the measurement from the sensors will have noise. So if you directly use numerical integration, it will amplify the noise. So in practical engineering, practice, we use a high-pass filter. It's basically just a derivative plus a low-pass filter. Yes? Yes. So this high-pass filter can be viewed as a derivative block. And then after the derivative block, we have a low-pass filter. So the derivative block is used to obtain the rate of change of your phi c. That's the function of S. After that, we pass the derivative measurement through a low-pass filter. Yeah. Yeah. So it's called high-pass filter. So it's or washout filter in many different terminologies. So. Yeah. Any questions about the design? Okay. So let's complete the design of the attitude control channel. Right? So we start with FD, then we eventually get the tau, the torque on the quadrotor. Okay, so this is background information about this arctangent 2 function. So this is the image of arctangent 2 function. And if we have y as a, and x as b. Then the arctangent 2 is a tangent. So this angle here is a tangent to a and b. Okay. So this nd is the desired lift direction. Yeah. So because the lift is perpendicular to the rotor plane, so this is our actual desired phi, or phi d or phi c. So same. So by using the arctangent 2, we can calculate this phi d. But be aware of in the ENU frame. So when you design your controller, you have to be very careful with the frame you choose. So in an ENU frame, this is actually a negative value. So after your arctangent 2, you should put at the negative side here. Good. Okay, so that's this is a position stabilization result of the 2D quadrotor control. So we move from the 0, 0 to 5, 0. And as you can see, y goes to 5. Z, oh, sorry, it's, yeah, so for apologies, so it's actually simulation from 0, 0 to 5, 0. It's not 5, 5. Okay. So the Z keeps at this 0 position. And as you can see, the phi here, it firstly has a negative phi because we need to move in the positive y direction. So it has a negative phi, so tilt right in the right direction. And then after almost reach the goal location here, so this is the goal location. So before reach goal location, it needs to decelerate. So we have a positive phi after the negative phi function. Makes sense, right? Good. So, any questions about the design of the position stabilization for 2D quadrotor? Is there everybody familiar? Okay. Okay, so then we proceed to the next. It's called path following control. So in the path following control, we consider a little bit more complicated model using the 3D drones, but also we make some simplifications. We assume that the quadrotor moves around the equilibrium, so every angle is small. So basically, the most significant change here is the attitude kinematics. So basically, so previously, if we have a body rate, and then the rate of change of the Euler angles is a nonlinear function of body rate. Okay, but if we make a small angle assumption, then it will converge to, then will just be simplified to a very straightforward, independent and linear relationship. So similar to the 2D case, so by this simplification, similar to a 2D case, we can separately design the channel in the x and y direction. So basically, it reduces 3D quadrotor to 2D quadrotors. So we just repeat what we've done in the 2D quadrotor twice. Okay. So I also built this model in Simulink. So you can download the Simulink model of this lecture. But beware that because I use the method built in rigid body block, this block use NED frame. So, but the principle is the same. So you just make there are some side changes in the control design, but the principle is the same. So because it simplifies my work, otherwise I need to rebuild all the process. So this is the dynamics of the quadrotor, a 3D quadrotor, and then this is the controller of the 3D quadrotor. And also, the controller is in the so-called cascade form. So we have a position control or the translational motion control block, which produce FD. And then the attitude control produce the tau and the F, the actual lift and tau. Okay, it's very similar to the 2D case. So yeah, so in this persistent stabilization channel, it's just PD controller. It's exactly the same as we have done in the 2D case. So we feedback the X and XD, calculate the error, and then what we do is combine with the velocity, and then we have a motion. We have a force to correct the position error. And of course, we need a saturation on the z-axis because the quadrotor cannot produce negative lift. So we need to saturate if the control signal is too large. Okay. Finally, we need to add a gravitation compensation force so that we have a lift. So that the FD consists of the correction force as well as the force to compensate for the gravity. So it's the same in the 2D case. Well, then for the attitude control channel, as I said, because we have a small angle assumption in our case, so it's it's meant for very slow movement of the quadrotor. What we do is that is follow the same idea, but do it twice. So the first step is still to get the magnitude of lift, right? So by doing the dot product and the square root to get the desired rotor lift provided by 4 rotors. Then by dividing the FD, we get ND to get a desired pointing, so the lift direction of the quadrotor. And same here is that, but something is different here. So as you can see, we have 2 arctangent tool blocks. So basically it means that in the phi channel and the theta channel, we use the arctangent tool of ends. So phi is like the arctangent tool of ends and y and z. So as you can see, phi is almost the same as the one we used in the 2D case. It's actually a dual of ny and nz. So basically, we have this angle, right? So we needed the quadrotor to tilt according to the lift in the y direction, and also in the x direction, we can do the same to calculate the desired angle, the pitching angle. And here, because we have a small angle assumption, so we just pick the yaw angle, the target yaw angle, as always be 0. You know, if it's not 0, then we need to do some transformation to get a theta phi and theta. But right now, if we have a small angle assumption, and also if we set the yaw to 0, then these 3 combine. By combining 3, we get the desired Euler angle. So this is omega c. So as you can see, what we do here is that I just repeat what we've done in 2D case twice, right? But in different channels because of the small angle assumption. Any questions? Okay, then after that, we pass the command Euler angles through the high pass filter again to get the rate estimation. And then after that, we apply the KP and the KD again. So the attitude controller is still a PD control. And now after that, this eventually gives us the tau in 3 directions to control the attitude of the quadrotor. Okay, I was clear. Questions? Yes.
Why do you make this small angle approximation?
Yeah, because if we do not make small angle approximation, you will end up dealing with this. Because the attitude motion is a nonlinear function of the rate. So if we do not make a small angle assumption, we need to design a much more complicated controller to take in the effect of this nonlinear relationship. So eventually, basically, it means that if the angle is very large, there is no easy relationship so that you can control phi, theta, and the yaw independently. So they are all coupled. by doing this assumption, we can design a very simplified controller by repeating the 2D case twice to get the controller in this decoupled form. So the purpose is to decouple the system so that we make our lives easier in terms of controller design.
So for path tracking, isn't this just applicable for like simple paths?
Yes, so I will expand later. It is suitable for straight line path following. So if you want to do more aggressive line, of course you need to have more sophisticated controller, nonlinear ones, to fulfill the task. Questions? Good? Okay. Okay, this is a simulation. Okay, so it goes to 5, 1, and 0. So as you can see, the system goes to our desired location. Okay, now the most complicated task we have in this lecture is the path following one. Okay. So basically, instead of command the quadrotor to fly to a given location, we want it to fly along a given path. So it means that we take off and hover at some location, and after that, okay, we want to fly eastwards at a speed of say 20 kilometers per hour. And how do we do that? So how can we do that easily based on our previous knowledge? Right? So we don't want to have too complicated to the design, so that, to force us to start from scratch over again. We want to utilize what we already have right now. So that's the path following controller I will introduce in the next slides. So before that, we need to have a description of the path following control problem. So basically, instead of tracking a curved path, so this is very complicated. So it will be discussed in 1217 next semester. Here we look at a simplified case where the path consists of a series of interconnected straight lines. And on these straight lines, the target velocity is a constant. So basically, we cruise at a different constant speed at different line segments. So by doing these assumptions, we can utilize what we already have to design a path following controller. So the first thing we do is that each path segment is defined by the so-called the starting point, which is pi. So the p is a starting point of the line segment, and also the line segment, the direction of the line segment is determined by ni. So basically, we have a series of lines connecting each other, and we define this trajectory by its starting point of each line and the direction of each line. Good. Okay. So what we do is that previously we want to for position stabilization task, we want the position error to converge to 0. But right now, it's not. We want the drone to converge to a line rather than a point. So in this case, we do not need the complete position error. We only need a part of it. So here, as we can see the geometry. So if we view this line from the starting point to the quadrotor as some kind of a position error, so this x minus pi, some kind of position error, we only want this perpendicular component to converge to 0. Right? So if the quadrotor slide around this line, it's fine, as long as it does not move away from the line segment. So in this case, our position error is no longer a easy subtraction. Is this position error from the starting point multiplied by this matrix? The reason why we have this matrix is that if we take a look at this segment, so if we do a perpendicular line that is perpendicular with our path, the projection, so the projection of this position error onto this line is given by this format. So basically, we do an inner product between our between the direction of the line and our position error to get a projection of the error onto the line, and then we time then it multiplied by the direction of this line to get this vectorized component.
And
Yes.
that is the direction vector of the path that you want to follow, right?
Yes.
Yeah.
So the direction of the path is set by the mission planner. Right? So you have some mission plan. So right now, this segment, as you can see, is the projection of the position error onto the path, and this part is not of our concern, because we want the quadrotor to be able to slide along the line. So this part can be arbitrarily large. We don't care. So then what we do is that, okay, so how, if we want to only keep this part, perpendicular part, what we do is that I use the original one, E, and then we subtract E by the projection of the position error. Then we can get the perpendicular component. So that's why we have a identity matrix here minus this. So it basically means that we have x minus xp pi minus and transpose x pi. So this will give you this. So basically, this is our complete path error, and because we do not care about where the drone is on the path, so we subtract the projection of the error onto the path, and remove that part, and then we get this remaining part, which only contains the perpendicular component. Now the controller is clear, and we want the perpendicular component to converge to 0 as time goes to infinity. Any questions? Good. And of course, we want while on this path, we want the quadrotor to have a constant cruise speed. So this is the VDI is VD is a scalar you can set, and this NI is as you can see, is the direction of our path, right? So then our desired velocity is VD times NI. So as time goes to infinity, we want this xi to go to 0 and our velocity to go to the VDI. And by simple algebra, we can say that if we take the inner product between our desired velocity and the path deviation error, then it is 0. It means that our desired velocity is perpendicular to our path deviation error. So these two is not going to affect each other. So we can freely set the speed without affecting the deviation of the path. Right? Yeah, this is a more detailed explanation. So this one is a projection of the path error onto the path. The position error onto the path, and by subtracting this component, we get a perpendicular component. So then our position error is in this format. We only care about the perpendicular component, and we have some kind of velocity error, which is our drone velocity subtracted by the desired velocity. So control goal is to design a U such that this two goes to infinity. This goes to 0 as time goes to infinity. Good. Okay. Okay. Here's a controller. So as you can see, I use almost the same structure of the position stabilization control. The only difference is that, okay, so we now have two inputs. One is P, so this one is P, the beginning of the path. Another is N times VD, so which is our desired velocity. And as you can see, the only modification we need to do is in the translation channel. So attitude channel, exactly the same. But translation channel, what we do here is that, okay, this part, as you can see, this is a identity matrix. So this matrix I minus n times n transpose. So we do a matrix multiplication of this and this to get the EXI. So this means that we multiply I minus n transpose with E, which is x minus p. And here, so previously in the position stabilization, we only feedback the VE, but right now because we have a velocity error, so we need to calculate the velocity error, and then we set a KD gain here. So this is the KP and KD. So this actually is a EV. So this one gives the EX. This one gives the EV. So as you can see, very small modifications compared with position stabilization control, right? We only modify the position error a little bit with the path definitions, and then we add a target velocity. Good. Any questions? So everything else after that is the same. Okay. Okay, this is a simulation result. So then as you can see, basically this is a magnitude of V. So it converges to the set point is 3 meters per second. And then this is a 3D drawing of the simulation of the path segment. So it starts from this location, and this red dotted line is a reference path. So it starts from this location and gradually converges to this desired path, and then it cruise along this path with 3 meters per second of cruise speed. Good. Okay. So then on top of that, if you want to design a mission planner, on top of that, what you do is that, okay, if we want to fly from point A to point B, then what we do is that we design a multiple set of PI and NI. And when it reaches the vicinity of this end of this segment, we switch the path command to another one. So then eventually your drone will just fly along this path consistent with straight lines. So if you want to a curved line tracking, by using this design, you can approximate your curved line by using a series of straight lines. So to approximate a curved line tracking control. Good. Any questions about this design and the overall idea? Good. So okay, so that's pretty much the summary of the control design for the drones, but in a very fundamental level. So because when we talk about the linearized controller and also PID tuning, and if you want the most systematic way to design the gains rather than rely on hand tuning, you can use LQR or pole placement. By using matter functions, basically you put your AB and QR matrix here, and it will give you the control input. So, but this will cover more detailedly in 12.17 next semester. Okay. So all the as we can see, because we use small angle approximation, so our design is only valid for quadrotors or multirotors, which moves relatively slow. So for example, if we want to drone to do surveillance or cargo transport, it's almost fine. So it works very good. But if you want to do something like a drone racing, because drone racing, as you can see, it flies very aggressively along a curved trajectory. So you need a more sophisticated long linear control. And also, if you want to add some more components on the drone to form some kind of VTOL or hybrid kind of flying vehicle. Of course, this it cannot be you cannot apply linear control on that. You need to rely on non-linear controllers.